Good evening, everyone. Welcome to Unacademy, India's largest learning platform, which is helping the students to realize their dreams in different areas, not only just in engineering, in the medical field, in the intermediate. Unacademy is working hard day and night and every day to see the success of the students. To see the success of the students. Okay. Now, the subject which I am dealing is electronic devices. The subject which is I am dealing with, this is electronic devices. So this subject comes under majorly for and electronics and communication engineering students, but also it will help for the students of EE to understand analog electronics, and for also instrumentation students also it will help the students to understand analog electronic concept. So this is not only just GATE, we're also teaching ESE. This is also for ESE, it will also help for ESE. This is lecture number 16. Now today in electronic device, we're going to discuss about what is the temperature effect on I naught. What is I naught, sir? Reverse saturation current. Reverse saturation current. And VF is forward voltage. VF is the forward voltage. VF is the forward voltage. So coming to my introduction, for those who have come for the first time, sir, myself, Shravan Kumar, I have master's degree from JNQH in VLSI system design. VLSI system design. I have 10 plus years of teaching experience. I have 10 plus years of teaching experience. The subjects which I can handle is EDC, that is electronic device and circuits, which we are discussing right now, and which will cover almost 10 to 12 marks, 10 to 12 marks in the gate examination, right? And analog electronics. So part of analog electronics is which I am discussing on Unacademy app. Unacademy app. You can log in and follow me on Unacademy app so that you can listen to all my analog electronics circuits class also, right? And I can teach another subject called digital electronics and EMFT. So just follow me for all these updates. So you can use a promo code. You can use a promo code called SVS10, SVS10, which will help you to get 10% discount, 10% discount on plus subscription, on plus subscription. What do you mean by plus subscription? What do you mean by plus subscription is a plus subscription student will get access to all the live classes, all the live classes. You can listen to the crash courses which are available on Unacademy app. Unacademy app. You will have this is very important. Time and again I'm mentioning. Time and again I'm mentioning. This is very important. That is weekly test. This is a weekly test, which is very important. This is very important. As I told you many times, and again I'm repeating. It is not just about what you. It is not just about what you read. GATE is all about how much you practice. How much you practice, which is very important. This is very important. After having a very weak test, you will know genuinely you will get progress, right? Now, this is another important thing, doubt solving session. Every fourth session is going to be doubt solving session. Every fourth session is going to be doubt solving session for you. And the classes will be in English and Hindi. Classes will be in English and Hindi, right? Those students who are not able to understand Hindi, they can listen in English. Those students who are not able to understand English, they can listen into the Hindi. This is another batch called rank improvement batch. For those who already got some good rank, so those who have already a very good foundation, and looking for to improve their rank, this is for them. This is for them, right? And this is what all about plus. And we have another subscription called iconic subscription. So what do you mean by iconic subscription is the first advantage of having iconic subscription is going to be a personal coach. A dedicated coach will be there for you. Dedicated coach will be there for you to guide everything, and he will tell you how to prepare. The preparation strategy he will tell you, and you'll have something called a study planner. study planner to track your performance. So how did you study? Where did you still how much you need to study? Everything will be there in the study planner. And study booster sessions. This is very important. This is also very important. You will have regular workshops and guidelines by the experts to improve your studies, to improve study. And you will have personalized test analysis. After every test, they will give you, right? They'll give you analysis for each and every question, and in-depth analysis will be given for each and every question, and you will be knowing where you are lacking and where to improve. Is that fine? It's fine. Then this another advantage is we are going to have is a preparatory study material will be provided. Preparatory study material will be provided. That is, specialized notes will be given and practice test will be there. This practice test will be there for iconic subscription. Iconic subscription. So for plus subscription, you have 12 months, 18 months, and 24 months. For 12-month subscription, you are going to have a fees of 27,225 rupees. This may be increased also. Just check in the app. You'll know what is the today's amount. So, but use this SVS 10 so that you'll get 10% discount. So that you'll get 10% discount on the value. 10% discount on the value. So for 18 months, you are going to have 34,650 rupees. And here also use SVS 10 as a promo code. You'll get 10% discount. For 24 months also, you have 39,600. So this is especially for those students who are in second year and third year. This 24, which will help a lot. So how can you pay? Simply you can pay by using your EMIs. You'll have EMI facility also. You have wallets, all the wallets, what you have, T wallet, which wallet, K wallet, all the wallets you can use. And you have a credit card facility also. Credit card facility also you have. So you can use you can pay using credit card. You can use paying credit card. Using the credit card, you can pay the amount. Okay. So this is for iconic batch. Iconic batch has only 12 months and 24 months. So this is also useful for CSE. All the coaching will be useful for GATE and ESE. For both GATE and ESE. So 12 month subscription, you have right now it is going to be 45,225 rupees. And you will get 10% discount after using a promo code of SVS10. SVS10. For 24 months, you are going to have 66,600. 66,600. And again, you can use this SVS10 as a promo code. SVS10 as a promo code. So this is another important step. You might have those who have not installed the Unacademy GATE Unacademy app. Just go to Play Store and type Unacademy Learning App. Simply you'll get this and install it. After installation, you will be asked to manage your goal. You have to choose your goal. You can see here CGPSC, MPSC, TNPSC, CSIR, UGC NET exam, NTA UGC NET exam, IIT JAM, NEET PG, like this. But our target is GATE and ESE. Choose your GATE and ESE. And then you have to select. You have 3 types of classes: plus classes, free course, and special courses. These 2 courses are free. But this plus subscription is very important. I think I have just now told you what are the advantages of plus subscription. And just simply click on get subscription. You will be allowed to get into the subscription. And this is a new batch which is started on 20th of this December, which will say a free special classes. So by name, know your basics, especially targeting GATE 2022 and 2023. GATE 2022 and 2023, sir. So what happens here is you will be given a complete roadmap for each and every subject of every branch, right? And understand the subject-wise strategy to crack. So subject-wise strategy to crack GATE 2022 and 2023. And you will be given an introduction and guidance by India's top educators in Unacademy across all the branches. So all the branches means you will have a mechanical engineering, civil engineering, electrical engineering, electronics and communication engineering, computer science and information technology engineering, chemical engineering. For all of you, we have this facility. For all of you, we have this facility. So please just download the app and see these classes. See these classes, very important. So this is one a new initiative by our Unacademy. New initiative by Unacademy. So Unacademy Combat. Unacademy Combat is already we have done one combat. The second combat exam, and for those who will get rank one will get some. We have exciting prizes. You will have a 3 months free subscription, or you'll give some Amazon voucher. You'll get if you get. Rank 4 to 50, you will be given 500 rupees Amazon voucher. So this will be on 29th of December. 29th of December on 6 p.m. 6 p.m. Now you can register, use the code to unlock. You will have your own code. You can use my code SVS10. You can use SVS10 the code to unlock your code. And what happens is this is India's largest fortnightly competition for GATE. Means for every 15 days you will have exam. For every 15 days you will have some exam. Every fortnight you will have some exam, right? So and then challenging GATE questions created by best educators. So this will be a very good practice test for your GATE 2021. Super fast and fun with real-time rankings. So ranks will be changing immediately after your answers. So you can have a lot of fun. You can see yourself. You can put yourself into pressure, and you can see how much successful you will be. So compete with the best. So you will have the teachers and everybody will be seeing. In a detailed video solutions by top educators. For every question, you will be given a video solution by top educators. And this is absolutely free, sir. Enrollment is free. Again, I'm repeating. This is on December 29th, 6 p.m. December 29th on 6 p.m. Now, just after this class, I request you to register for this. So this is another same I'm talking about. Same thing I'm talking about. The Unacademy Combat. Enroll for free. So the combat will be on December 29th, 6 p.m. December 29th on 6 p.m. December 29th on 6 p.m. Just register immediately after the class. And I wish you all the best. Hope you'll get into 1 to 3 or 4 to 50 ranks, at least 50 ranks, top 50 ranks. Right? I wish you all the best. Okay, we'll move on. So I request all of you to just follow me on Unacademy. So Unacademy is so this is what https /unacademy.com/Unacademy user Z614A9LLPDQQ. So this will be there in my notes. I'm posting it on all my class notes will be posted on. All my class notes will be posted on Telegram channel. You can see the document, and you can follow me on Unacademy. Yeah. So today's topic is going to be effect of temperature on reverse saturation current. Before starting today's topic, just go back and see what we discussed in the previous class. So we started our discussion with what is PN junction reverse bias. What do you mean by PN junction reverse bias? What do you mean by PN junction? It's very simple, sir. The negative terminal of the battery, is connected to the positive terminal P-type material of the semiconductor. That's PN junction. The positive terminal of the battery is connected to N-type of the PN junction diode. Then that is called reverse bias. This is called reverse bias. So what happens in the reverse bias? So it attracts the holes, the P region. Now what happens is, now it attracts all the holes are attracted by the negative terminal of the battery. Electrons in the N region are attracted by the positive terminal of the battery. So they will move away from the junction. The majority charge carriers will move away from the junction. When they are moving away from the junction, what happens there? The width of the depletion region is increased. So what do you mean by how can you measure this value of width of the depletion region? So the width of depletion region is going to be square root of 2 epsilon by q into 1 by nd plus 1 by na into v plus vr into v plus vr. This is the formula. As the vr is increasing, double increases. As the reverse voltage is increasing, double increases. Double increases. But there exists a small current which is because of minority charge carrier current. What is the minority charge carriers in n region, sir? Holes. What are the minority charge carriers in p regions are electrons. So these minority charge carriers electrons will be repelled by the negative terminal of the battery, and here the holes which are the minority charge carriers will be repelled by the positive terminal of the battery. So slowly they will move towards the junction. Slowly they will move towards the junction, because of which a small current will flow. Because of which a small current will flow, and that current is called reverse saturation current. That current is called reverse saturation current. That current is called reverse saturation current. And now we discuss something called current components in a PN junction diode. Current components in a PN junction diode. So see what there will be two currents in a given p type or n type. So one is because of hole current, other one is because of electrons. So if this IPP is nothing but hole current in p region, and this IPN is nothing but hole current in n region. Similarly, INN is nothing but electron current in n region, and INP is electron current in p region. So at any given point, the total current is a summation of majority charge carrier current plus minority charge carrier current. Majority charge carrier current and minority charge carrier current. That is IP. This current in a P type region is going to be summation of IPP plus INP. IPP plus INP. Similarly, this current is nothing but INN plus IPN. At the junction, your current will be IPN naught plus INP naught. IPN naught plus INP naught at the junction. X is equal to 0. X is equal to 0. The total current is going to be what I told you is IPN naught plus INP naught. IPN naught plus INP naught. Then here comes the law of junction. So what do you mean by law of junction is, the law of junction explains, this is P dash of n of 0 is going to be Pn naught into e power v by vt. What is this? What is this, sir? This is P, that is electron concentration. Electron concentration in n region, which is varying with respect to distance. Varying with respect to distance. So what is the distance is measured is x. X is a variable. So x is equal to 0 means at the junction. So at the junction, the electrons are the holes in the n region. Holes in the n region is going to be, this is what is Pn naught. Pn naught is the concentration of holes in n region at equilibrium position. Is equal to into e power v by vt. Similarly, electrons in p region at the junction is going to be np naught into e power v by vt. So this equation is very important. Now here comes the diode current equation. So by considering the law of junction, we'll derive what is diode current equation. The diode current equation is very important. This diode current equation is equal to I is equal to I naught into e power v by vt minus 1. I naught into e power v by vt minus 1. What is I naught? I naught is a reverse saturation current. Just now we discussed yes or no? What is reverse saturation current we have discussed? What does it mean by reverse saturation current. This is a formula, sir. Many problems are asked in the previous gate examinations also based on this formula only. This is what is saying. So eta is also eta is considered because of the recombination and the generation of the charge carriers. We earlier we considered that equation by thinking that it is constant. I is constant, but it varies by changing the value of this value. I mean, it changes because of the regeneration and uh, generation recombination. Okay. So eta is equal to constant and 1 for germanium and 2 for silicon. 1 for germanium. This is you have to remember, because in the given problems you will not be given this values in general. But remember, eta is equal to 1 for germanium, 2 for silicon. 2 for silicon. So this is what the diode current equation. And volt ampere characteristics we have discussed. So what volt ampere characteristics means? So voltage versus current. Voltage versus characteristics of a diode. So for positive for forward direction, for forward characteristics, so how they look like is, so you can see here till some point of time that there is no conduction. After crossing some voltage only the conduction starts, and that voltage at which conduction started is called cut-in voltage. And after cut-in voltage, the diode current increases exponentially. It is forward current IF, forward current, which is in terms of milliamperes. And applied voltage will be in volts. Applied voltage will be in applied voltage. And VF stands for forward voltage which you are applying. Is it clear? Reverse characteristics of a PN junction diode. I need not explain you again and again. So what reverse characteristics is very simple, sir. Very simple. Because of when the diode is reverse biased, because this I0 represents minority charge carriers current. I0 represents minority charge carrier current. We also call it as reverse saturation current. Which will be in terms of microamperes. And this is the complete VI characteristics of a PN junction diode. This is forward bias and this is reverse bias. So forward bias and reverse bias. You can see here this cut-in voltage is for germanium. The germanium cut-in voltage is going to be 0.3 volts. For silicon, it's going to be 0.7 volts. As I told you, some textbooks will follow germanium as a 0.2 volts and silicon as a 0.7 volts. Nothing wrong. But remember always, the forward current IF is very high when compared with the reverse current IR. And you can also see some conclusions we have written. The first conclusion is silicon requires more cut-in voltage to start the conduction when compared with germanium. You can see here silicon needs 0.7 volts or 0.6 volts for the conduction, whereas germanium needs only 0.3 volts or 0.2 volts, right? Another important point is the reverse saturation current of silicon is very small when compared with germanium. Yes, the reverse saturation current also, you can see here, the reverse saturation current is in nanoamperes. In reverse saturation current is nanoampere for silicon and in microamperes for germanium. I think this is what we discussed in the previous class. We will start our today's class. So in today's class, now let us consider. We know that when I'm talking about reverse saturation current, it means the diode is reverse biased. As we know, there exists a current. When the diode is reverse biased, there exists a current because of the minority charge carriers in N region. The current in P region when P region edge, I should say edge, P region edge, when the diode is reverse biased. Diode is reverse biased. Diode is reverse biased. So what is that, sir? What is that, sir? Yesterday we have derived. That is I P n of 0 is equal to IPN of 0 is equal to A Q dp AQ dp into Pn naught by LP into e power V by Vt e power V by Vt minus 1. Similarly, we know that INP naught, INP of 0 is going to be A Q, we'll get Dn here, and NP naught by ln into e power V by Vt minus 1. So what is this dp, sir? Dp is nothing but diffusion constant. What is LP, sir? What is LP? Length of diffusion of the hole. And what is Pn naught? Pn naught is the electron whole concentration in n region. Whole concentration in n region at equilibrium. Then what is V? V is applied voltage. Vt is temperature equivalent voltage. Volt equivalent temperature I can call. Volt equivalent temperature. Similarly here, A is the area of cross section, Q is the charge, Dn is diffusion constant of electrons or n-type, diffusion constant in n-type. What's NP naught? This is NP naught is nothing but number of electrons in P region at equilibrium. Then what is Ln? Ln is the length of diffusion of an electron. Or in n region, I should say, actually. Length of diffusion in n region. Again, e power V by Vt, E is applied voltage or voltage across the diode which you are applying, or Vt is volt equivalent temperature. Okay. Now the total current, what it will be? Total current I is equal to IPN of 0 plus INP of 0. IPN of 0 plus INP of 0. Now substitute them from the previous discussion. I is equal to, this is AQ dp Pn naught by LP into, so e power V by Vt minus 1 plus INP naught. What is INP naught? This is also A Q dp NP naught by ln into e power V by Vt minus 1. Yes or no? Just simply from previous discussion only I am trying to write. Now what I'll try to do is here, I'll take out this common, e power V by Vt is common. So I can write I is equal to A Q dp AQ dP Pn naught by LP plus AQ dN. So this is dN, sir. dN into NP naught by Ln, and then you can take out e power V by Vt minus 1. Sir, is it not I is equal to I naught into e power V by Vt minus 1? What is the formula? Is it not the formula of current? Is it not the formula of current? So what is then I naught? What is then I naught from this? From this, I naught is equal to A Q dP into Pn naught by LP plus A Q dN into NP naught by Ln. NQ naught by Ln. Yes or no? No. Yes or no? No. Then what is from mass action law? From mass action law. From mass action law, what we can say, sir? We can say Pn is equal to Ni square by Nd, and then Np is equal to Ni square by Na. Na square by Na. Na square by Na. Now substitute this Pn naught and Np naught. Pn naught and Np naught. So what you'll get is I naught is equal to A Q dP by LP into Ni square by Nd plus here A Q dN by ln into Ni square by Na. If you want a separation, you can separate here. So I naught is equal to this. This is what we got. This is what we got. But our from what we know, but we know that sir, we have derived an equation for Na square. Na square of intrinsic concentration. We have derived an equation. Na square is equal to A naught into T cube into e power minus Eg naught by Kt. This is what we have derived. Is not by Kt. Now substitute this in the above equation. Substitute this in the above equation. What you will get again? What you will get again here? I'll simply write here. Right here, I naught is equal to with this some with this is going to be A Q dP by LP into, I can write actually LP into Nd plus AQ dN by ln into Na. Are you sleeping, sir? Huh? No, right? This is derivation, important derivation. You should understand the derivation. You should understand the derivation. That is the reason why I am trying to draw. I am trying to write each and every step. You should not sleep. Understand every derivation. Every derivation is important. If you understand derivation, you will be very good at the basics of the subject. You should also know the definition. I mean every derivation. But it's n square, I'll substitute here, is going to be a naught into t cube into e power minus eg naught by kt. Eg naught by kt. So assume that this everything is already constant. A is constant, Q is constant, dp is constant, lp is constant, nd is constant, dn is constant, ln is constant, na is constant, a naught is constant. So assuming all these things are constants, so I naught is going to be what, sir? Let's assume another constant k. Let's say some constant k1. Already k is existing here, so let's assume another constant k, right? If it is constant k, so what it will be is you're going to have t power m. This is the expression, very important expression. T power m into e power minus eg naught by kt. Eg naught by kt. Or what you can do, sir? Or you can do is you can divide this with k q, and you can also divide this q, or you can write this as I naught is equal to k1 into t power m into e power minus vg naught by vt, where m is equal to 2 for germanium and 1 for silicon. 1.5 for silicon. Remember this point. Sir, by again considering generation and recombination, that I naught is equal to k1, that is constant k1 into t power m. I have already done what is m, e power minus vg naught by eta vt. Is a very important expression, for reverse saturation current. So where k1 is constant, m is the value which we have written, vg naught, eta vt. So you should also know what is eta, just we have written. What is vg naught? What is vg naught? Vg naught is equal to now for germanium it is going to be 0.785. For silicon it is going to be 1.21 volts. It is also volts, not electron volts is eg naught. Electron volts is nothing but eg naught, right? So now what you do is here, apply logarithm on both sides. Apply logarithm on both sides. If you apply logarithm on both sides, now what happens, sir? Ln of I naught is equal to ln of k1 k1 plus, shall I directly write, this is going to be m into log of t, mln of t. I will directly write this. And then this is going to be minus e power. So I'll simply write. I can write this is going to be vg naught by eta vt. I have directly written that. Applying logarithm on both sides, what you will get here is, so ln of I naught is equal to ln of k1 plus m into ln of t. If you want me to write again, I'll write it here because you may not get it properly. Sometimes when the system is saving the software, ln of t minus vg naught by eta vt. eta Vt. Now what you do is differentiate the above equation with respect to t. Differentiate the above equation. Differentiate the above equation. With respect to t, capital T. So d by dt of, sorry, capital T, d by dt of logarithm of I naught is equal to d by dt of this logarithm k1 plus m is constant. We'll get d by dt of a natural logarithm of t minus 1 by eta. 1 by eta is constant. Now what can I do is, Vg naught is also constant. So this is going to be Vg naught, then d by dt. What is Vt, sir? Vt is simply kt by q. I can say simply it's going to be q by kt. Of course, this q is also constant. This q is also constant. This k is also constant. So I can bring it out. I can bring it out here. Now what we'll get is it not 1 by I naught into d I naught by dt? Yes, this is constant. You'll get 0 here plus m here. So what is natural logarithm of this? What you'll get, sir? You'll get t or not, 1 by t or not. You'll get 1 by t here. You get 1 by t here. Then minus Vg naught by Vg naught q by eta k into, sir, 1 by t, d by dt of 1 by t. Is it not 1 by t square? Is it not 1 by t square? Is it not, that is minus 1 by t square, sorry. Is it not 1 by t square minus 1 by t square? Correct. So what I am going to get is di naught by di naught by I naught by dt is equal to m by t plus Vg naught by eta k t by q into 1 by t. Kt by q into 1 by t. So here what I'll try to write it again. di naught by I naught by dt is equal to m by t plus Vg naught by eta. Go back and see. Can I write this as a t into Vt? Tvt. This is very important formula. This is important formula to be remembered. So this di, what is di naught by I naught? Di by naught I naught is a fractional change. In reverse saturation current. Reverse saturation current. You know the value of m. You know the value of t. T is nothing but temperature. Vg naught you already know. VG naught you already know. VG naught you already know for given silicon. Eta you know, T is equal to. So substitute all the values for germanium. Now for germanium, so what is the value of M? M is equal to 2, right? VG naught is going to be, what is VG naught, sir? 0.785 volts. Eta is equal to how much? Eta is equal to how much, sir? For germanium, it is going to be 1. And T, consider it as 300, and VT as 26 millivolts. 26 millivolts. Substitute all of them, sir. Let's see what you are going to get. Let's see what you are going to get. For germanium, this di naught by I naught by dt, what you will get, sir? So M is going to be 2 by 300 plus 0.785 by eta is going to be 1 into 300 into 0.026. If you substitute this, you'll get approximately, I think you'll get approximately how much you'll get it, sir? You'll get 0.11. 0.11 is going to be for every, this is a fractional change, right? Fractional change in current, reverse saturation current for every 1 degree change in dt. So per every degree centigrade change. Now similarly, that means what it means for every 1 degree. So what it means is for every 1 degree rise in temperature, for every 1 degree rise in temperature, the reverse saturation current, the I naught, the reverse saturation current of germanium will increase by 11%. But it will increase by 11%. Increase by 11%, which is very important, sir. Which is very important. That is the reason why I am writing with some other color. Similarly, if you calculate for, silicon, calculate what is M is going to be 1.5. N is going to be how much? Eta is going to be how much, sir? Eta is going to be how much? Eta is going to be 2 for germanium. What will be remaining? VG naught is going to be 1.21. And then T is 300 and this remaining two are same. T is 300 and what is the other one, sir? VT is going to be 26 millivolts. Now how much you will get it here, sir? Di naught by dt is equal to M is 1.5 by 300 plus VG naught is going to be 1.21 by 2 into 300 into 26 millivolts, 26 into 10 to the power of minus 3, I can say. So how much you'll get? You'll get is approximately 0.08%, 0.08 per degree centigrade. 0.08 degree centigrade. So what do you mean then? This represents, this says what it is saying, sir? It is saying that for every 1 degree rise in temperature, for every 1 degree rise in temperature, every 1 degree rise in temperature, the I naught of silicon changes by an amount of by an amount of 8%. 8%. This is very important. No, but practically what happens is, for practical use, experimentally, that is practically experimentally, sir, power has gone. I am running on UPS. Just bear with the sound. Please just bear with the sound. Experimentally, it is proved that for proved that the reverse saturation current I naught increases by 7% per degree rise in temperature per degree rise in temperature for both silicon and germanium. For both silicon and germanium. This is a very important point which we need to consider. So how much, sir? This is 7%. Practically this is 7%. Theoretically what we got is 8% for germanium, for silicon, and 11% for germanium. But practically, experimentally what it is proved that, experimentally it is proved that I naught increases by 7% per degree rise in temperature for both silicon and germanium. Right? Now here comes when will it doubles? When will this reverse saturation current doubles? So it is very important. Note here, the reverse saturation current I naught doubles per every 10 degree rise in temperature. 10 degrees rise in temperature. How, sir? For every 1 degree, how much is it increasing? 7% means simply 1 plus 0.7 whole power 10. How much you'll get? Approximately you'll get 2. So for every 1 degree rise in temperature, reverse saturation current doubles. So if you want to express it in mathematically, so mathematically, we want to express in mathematically. So mathematically, what happens, sir, is the new reverse saturation current I naught 2 is equal to 2 power T2 minus T1 by 10 into I01, or you can write 2 delta T by 10 into I01. This is I02. The new reverse saturation current is I02. You will get many problems from this. very important, very important, very important. I naught 2 is equal to 2 power delta t by 10. You substitute if you whatever you want. If delta t is 10, delta t is 10, so 2 power 10 by 10. If delta t is 10, what happens, sir? I naught 2 is equal to 2 power 10 by 10 into t01. That is 2 into I01. Sorry, I01. So I naught 2 is going to be 2 into 10 power 1. I naught 2 is equal to 2 into 10 power 1. 2 into 10 power 1. Okay. So this is very important formula. This is a very important formula. We'll discuss some problems based on this. We'll discuss some problems based on this. You need not worry. We'll discuss some problems based on this. Okay. Now moving on to the next topic, effect of temperature and forward voltage. So far we have seen how the reverse saturation current changes with respect to temperature. Now we will see effect of temperature on forward voltage Vf, on forward voltage Vf, on forward voltage Vf, on forward voltage Vf. Okay. Now consider same reverse saturation current I naught, reverse saturation current I naught is equal to what we have done, sir? K1 into T power m into e power minus Vg naught by eta Vt, what we have discussed. Eta Vt is what we have got. I naught is equal to K into T power m into e power minus Vg naught by eta Vt. Vg naught by eta Vt. What we know, sir? We already know. We know that I, what is I? I is a current, diode current. I is equal to I naught into e power V by Vt minus 1, or you can still say it is e power, if you want to write e power V by eta Vt minus 1, we know. You just substitute this in the above, I not in the above equation. You substitute this in the above equation, and by neglecting 1, you will get I is equal to I naught into e power V by eta Vt. Substitute this equation number 1 in equation number 2. Substitute 1 into what you will get, sir? Substitute 1 into what you will get, sir? So I is equal to K1 T power m into e power minus Vg naught by eta Vt into e power V by eta Vt. So I can simply write this going to be K1 into T power m into e power V minus Vg naught by eta Vt. Power has come. Very happy that power has come. Just a minute. Just a minute, sir. It's good that power has come. It's good that power has come. So this is going to be K1 into T power m into e power V minus Vg naught by eta Vt. Eta Vt. Right? So this is going to be I, current I. Now what I have to do is, I have to do something that if the current is constant, if the diode current is constant, as diode current is constant, as diode current is constant, as diode current is constant, I mean, what we are thinking that diode current is constant and voltage is varying. That's what, right? when with respect temperature, right? So di by dt must be equal to 0. Yes or no? The diode current is constant, di by dt is going to be 0. So if this, let's say this is going to be equation number 3. So now differentiate on equation number 3. Again, differentiate equation number 3 with respect to t. Differentiate equation number 3 with respect to t. So what it happens, sir? What will happen, sir? di by dt is equal to you can see here t and v both are variables. T and v are both are variables. K is constant, so no problem. K will come out. But so here you need to apply UV formula. UV dash plus VU dash. UV dash plus VU dash. Yes or no? So then first let's do this then. So m, this is t power m means m into t power m minus 1. Yes or no? Simply it's going to be, I'll directly write, sir. Is it fine? Is that fine? I'll directly write m into t power m minus 1 into e power e g naught means it will be constant. So no issues. E power v minus vg naught by eta vt will be same, plus t power m will be same. T power m will be same or not? T power m into, now I'll write this d by dt. I'll let you know why I'm writing like this. E power v minus vg naught by eta vt. Sir, e power x, d by dt of e power x, e power x into dx by dt, Now, in the second step, I can write k1 into, sir, this is bit tedious process, but you need to do, sir, nothing wrong. Yes, this is tedious process, but you should practice. Just you should understand what I am trying to do. This is minus 1. This is a t power m minus 1. Sometimes you may get confused. This is not writing. So e power v minus vg naught by eta vt plus t power m will be there. E power x is nothing but e power x. E power v minus vg naught by eta vt. Again, this is d by dt of v minus vg naught by eta vt. So I can still write this is going to be, I'll take this e power v minus vg naught out common. I'll take this as a common. And this is also, I'll take t power m also common. So what will be remaining, sir? K1 into t power m into e power v minus vg naught by eta vt to take common. So what will be remaining? It will just m by t plus, here I have taken common out. Sir, you can see here this is u by v formula. This is u by why sir this is I wanted achar. I'll do one thing. I'll write this as d by dt of v minus vg naught by eta k t by q. Now this is super di by dt is equal to K1 into T power M into e power V minus Vg naught by N into Vt, and here comes M by T plus, now UV dash plus VU dash, UV dash plus VU dash, right? So shall I write in the, now here I'll write so that you will get very clearly. So what will be remaining, sir? What will be remaining? I'll do one thing. I'll do only this thing. Here plus of this is n cube, nk by q is common. Take it out. Take it out. So what happens, sir? Again, this is going to be 1 by nk by q into so t is constant, u dash is going to be dv by dt minus this v minus vg into t. Simply will get v minus vg naught into 1 will get into 1, which will get 1 by t is nothing but minus 1 by t square will get minus 1 by t square or not. D by dt of 1 by t. D by dt of 1 by t, what will get? D by dt of 1 by t, what will get, sir? 1 by t square. Yes or no? You'll get 1 by t square. You get 1 by t square. Now substitute again here, you'll get di by dt, this again everything is common. If you re-simplify this, what you'll get is k into t power m into e power v minus vg naught by kt eta vt into so what you got is m by t plus 1 by eta k by q into you'll get t minus t dv dt minus of t dv dt minus v minus vg. This is v minus vg. V minus vg naught will get. It is not looking good, but still, this is a lengthy expression. This is a lengthy expression which we need to get. But what we know, di by dt must be equal to 0. That's what we discussed, right? Di by dt is equal to 0. This all will get cancelled. Only this portion we need to do it. 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 Now, if you do it, what happens is, what in the next expression, I'll do it is simply what you'll get is, I'll directly write m eta vt plus t dv by dt minus of v minus vg naught is equal to 0. What will get? So simply don't think what I have done. I have taken what I have done. Eta kt by q. Eta kt by 2. What I have taken? Just I have cross multiplied this. And what I got is m eta vt. This is kt by q. What will get? Kt by q. What is get? Plus t into dv by dt minus v minus vg naught is equal to 0. So from this, I need what, sir? I need this dv by dt or not? Because our point of discussion is what? Temperature. Effect of temperature on the applied voltage Vf or forward voltage Vf. So now from this, what I need is dV by dt. dV by dt is equal to, what I should write? Shall I write directly? Shall I write directly? Or you want me to wait? Huh? Or you want everything to be same? So okay, what I'll do is, for your sake, it's going to be dV by dt, dV by dt, V minus Vg naught minus M eta Vt, eta Vt. So I can write dV by dt, dV by dt is equal to V minus of Vg naught plus M eta Vt by T is by T. This is very important formula. So change in voltage with respect to temperature is coming very cross. No? I have written very cross. Change in voltage with respect to temperature. Change in voltage with respect to temperature. Change in voltage with respect to temperature. Now for germanium and silicon, we'll see. So for germanium, we'll see. So everything is everything you know. Vg naught is how much, sir? Vg naught is going to be 0.785 volts. M is going to be how much? M is going to be how much? M is going to be how much for germanium? 2. Eta is going to be 1, and Vt is going to be 26 millivolts. 26 millivolts. The T is equal to 300, and assume V is going to be 0.2 volts. That's cut-in voltage or 0.2 volts. So how much you will get dV by dt? dV by dt. So dV by dt, substitute all the values, you will get 0.2 minus, so Vg naught is going to be 0.785 plus M is how much, sir? M is how much? You will get 2, eta is going to be 1, then Vt is you got, it's going to do 26 into 10 to the power of minus 3 by entire thing by 300. You know how much you'll get? You'll get dV by dt. dV by dt is going to be minus 2.12 millivolts per degree rise in temperature. This is for germanium. What does it mean? What does it mean? This negative sign indicates, indicates the negative sign indicates that for every 1 degree rise in temperature, for every 1 degree rise in temperature, the cut-in voltage, the voltage required for the conduction will be decreased. The V is decreased by V cut-in is decreased by 2.12 millivolts. 2.12 millivolts. Very important. This is very important. You should remember this point. For negative sign indicates that for every rise in temperature, the cut-in voltage, the V cut-in voltage is decreased by. It means what, sir? Let's say now cut-in is happening. 2.12 can I write this as a 0.0 milli 10 to the power of minus 3, 0.212 volts. Let's say example I'll tell you. Example I will tell you. Example I will tell you. Let's say for germanium, let's say V cut in is going to be 0. 0. Let's say 212 volts at T is equal to, example I'm saying, 333 degrees Kelvin or degree centigrade or Kelvins, let's say, right? So at T is equal to 334 degrees Kelvin, we need only that is 0.212 minus 0.002 approximately I'll take. So how much you need? 0.210 volts only for cutting voltage. So cutting is happening. What does it mean? What does it mean? So earlier the cut-in was happening here. Let's say some voltage here. So the next time when the temperature is increasing, cut-in is happening before that only. So this is at 333 degrees. So this is happening at 334 degrees. So for every 1 degree rise in temperature, the cut-in voltage decreases. The cut-in voltage decreases. The cut-in voltage decreases. Similarly, for silicon, dV by dt is going to be 2.3 millivolts per degree centigrade. But practically, this is important point to be remembered. Practically, for both germanium and silicon, dV by dt is going to be minus, this also minus, minus 2.5 millivolts per degree centigrade. Very important to be remembered. This is very important to be remembered. Very important, sir. Very important. Some problems will be, we will solve some problems based on this. We'll solve some problems based on this. Okay. We'll solve some problems based on this. Just a second. Okay. We'll solve some problem based on this in the next class. Hopefully. Huh? Right. Now we will continue our discussion. So here comes something called, very importantly, diode resistances. Diode resistances. What do you mean by diode resistances? The resistance offered by diode in forward bias condition is called forward resistance. You may get it out, sir. Is the diode offers the resistance when it is forward? Yes, 100% it is not conducting. 100% is not conducting. Still some resistance exists. And that resistance is called forward resistance. But that forward resistance is of in two ways. One is called static, other one is called dynamic. So static resistance is static forward resistance is represented with capital R, capital F, and dynamic or AC. The static diode resistance is also called a DC forward resistance. Dynamic or AC forward resistance is called small r suffix small f. Smaller suffix small f. Now we will try to see what does it mean. Do not worry. So first you can see here. What is this? You can see it here. To take 2 points on the given graph. Let's say A, B, C, D. Right? A is a voltage and the corresponding current is going to be C. So B is next voltage, its corresponding current is going to be D. Its corresponding current is going to be D. So the difference in this voltage is nothing but delta V, difference in current, right? For this much change in the voltage, there is a this much change in the current. This much change in the current. That is dynamic resistance that we'll discuss now. So before that, we'll discuss static resistance. What is static resistance is? The static resistance RF is defined as the ratio of the DC voltage applied across the PN junction to the DC current flowing through the PN junction. That is, you take any point. You take any point. That's he's saying. He's taking. Consider a point E. Consider a point E. Consider a point E. So this is the voltage applied. This is the voltage applied. So this OA is the voltage applied, and OC is the current you got, or OB is the voltage applied, and OD is the current you got. So what he's saying is, so OA by OC is at point E. If you want to calculate at F, from graph you are consider OB by OD. It's going to be OB by OD at point F. You can consider at any point. You can consider that RF at any point. You can consider it at any point. So OB by OD at point F. OB by OD at point F is nothing but static forward resistance. Then what is dynamic resistance? Dynamic resistance is nothing but the dynamic resistance offered by PN junction diode under AC conditions is called dynamic resistance and is denoted by RF. That is, the dynamic resistance is defined as the reciprocal of the slope of the VI characteristic. That is dV by dI. So dynamic resistance is not constant but depends on the operating voltage. Depends on the operating voltage. It means, so from the graph, what is saying, sir? dV by dI. So you can say AB by CD. Change in voltage with respect to change in time. First, change in current, or change in current with respect to change in voltage. Change in current is respect to change in voltage. But as it is a resistance, we are doing it. Right? The slope, inverse slope of the, so the reciprocal of the slope of the VI characteristics is nothing but dynamic resistance. This is also you need to remember, right? Whereas static resistance, what is static resistance? Static resistance simply is forward DC voltage by forward DC current. So you can take it at any point. But here this is AC current. This is applied for AC conditions. AC input is applied. For AC input applied, we'll get dynamic forward resistance. Or simply we can call AC forward resistance nothing but dynamic forward resistance. Right? So here one point you need to consider here is, so we know that so how can you say that this is the dynamic resistance is not a constant but depends upon the operating voltage. That we'll see now. Now consider I is equal to I naught into e power V by eta Vt minus 1. V by eta Vt minus 1, yes or no? V by eta Vt minus 1, yes or no? So now what we want? We want simply dV by di. Yes or no? dV by di. So but I have I. So simply I'll differentiate this with respect to V. Differentiate with respect to V. So I'm trying to say di by dV. Di by dV is equal to I naught into, again this is what, sir? E power x. Simply it's going to be e power V by eta Vt into what will get, sir? It is one, this is V. So you get 1 by eta Vt, what you will get. So I can write this going to be I naught into e power V by eta Vt by eta Vt. Sir, simply you should get differentiation. Nothing else is here. Nothing else is here. E power x d by d of d by dx of e power x. D by d of e power x is equal to e power x. And but whatever is existing is here, some function is existing. Because of that, one by eta Vt. This is constant we got. Let's say e power ax. E power ax nothing but a e power x. Right? A e power x. Yes or no? Yes or no? Whether you got it or not. Huh? The formula. This is the formula which we have discussed. So intermediate foundation. Di by dv is going to be di by dv is going to be I naught into e power v by eta vt. E power v by eta vt by eta vt. Eta vt is now what we got. Now eta. Sir, can I write this from this equation from equation 1 I naught into e power v by eta vt can be written as I plus I naught. So di by dv can be written as I plus I naught by eta vt. I plus I naught by eta vt. I plus I naught by eta vt. But I naught is far less than I. So di by dv is going to be simply I by eta vt. But what we need dvi by d, what we need is we need dv by di. So that is going to be eta vt by I. Eta vt by I. Eta vt by I. So this is the important formula, sir. This is important formula. Remember this formula. Remember this formula. This formula is very important. Many questions will be asked. You might be thinking, sir, everything is saying important. Everything is, yes, sir, everything is important. Everything is important. Everything is important for gate exam. For every mark, there will be a lot of change. There will be a lot of change. There will be a lot of change. So I would request all of you to remember all these things. So the RF, or if you want me to write RF in a different way, I'll write in RF. The RF, the forward dynamic resistance is going to be dV by di, which is equal to eta Vt by I. Eta Vt by I. Right? Or if you want to write in some different way, RF is equal to 1 by di by dV. Di by dV is nothing but 1 by slope of forward characteristics. Slope of forward characteristics. So this is going to be 1 by slope of forward characteristics. I'll write here 1. I'll rub this 1 so that no confusion. If you know the slope of the forward bias characteristics, then you can calculate RF very easily because it's simply reciprocal of that. It is simply reciprocal of that. It's simply reciprocal of that. So if you want to calculate from the graph, it is very simple. So from the graph, if you want to calculate, it's very simple. RF is going to be delta C dV by di. Very simple. Delta V by delta I, that is equal to AB by CD from the graph. I am talking about from this AB, delta V by delta I, delta V by delta I. Okay. Now it is a reverse resistance of a diode. So far we have discussed forward resistance of a diode, Now we will discuss the reverse resistance of a diode. So what do you mean by reverse resistance of a diode? Same. The resistance offered by the diode in reverse biased condition. In reversed biased condition is called reverse resistance. It's called reverse resistance. Again, there are two types of resistances: static resistance (RR), dynamic resistance (RR), small r. RR. So not it is RRR. The film which you are thinking about is only 2 R's, right? I think still you have a lot of time for triple R, RRR, right? You need not worry, right? Reverse resistance, right? First think about this reverse resistance. That RRR, if you watch RRR, you will not get anything. Waste of time. What will you get? Will it help you to get some 1 mark in gate? No, you will not get any one. Even single mark also you will not get. Will you get it, sir? No. Oh, concentrate on here in reverse resistance, which will help for gate examination. Okay. Now, this is the reverse characteristics. Which we have already discussed. So first then, static reverse resistance RR is nothing but the static reverse resistance RR is defined as the ratio of the applied DC voltage to the reverse saturation current I0 flowing through the diode, flowing through the PN junction diode. Very simple. Always this is applied voltage by resistance, current. Sorry, applied voltage by current. So OQ by OR. You can go and see here. It is this OQ by OR. OQ by OR. This gives a static resistance. So OQ by OR gives you a static resistance, right? Applied voltage by applied reverse current which you got. Okay. So what is dynamic resistance? Dynamic resistance RR. Dynamic resistance RR is nothing but the reverse dynamic resistance RR is defined as the ratio. I think Malay ratio, but ratio of the incremental change in reverse voltage applied to the corresponding change in reverse current. So change in reverse voltage by change in reverse current. Very simple. Same. That is also same, right? Earlier also. So here change in reverse current for change in voltage. So in this region, you can see here in this region, delta VR is some let's say 0.2 volts. 0.2 volts or something, let's say 2 volts. But how much is change in the current? Change in current is 0. No current change. Current is constant. You got current is constant. So how much is resistance you'll get? So change in voltage by change in current. Change in voltage by change in current. How much reverse resistance you will get, sir? Can somebody tell me? Comment, tell me. It is going to be high, very high. So here, for example, I am saying RR is going to be, let's say 2 volts by 0. So RR is going to be infinite. So the dynamic reverse resistance can be infinite. Practically it is not, theoretically it is correct actually, but practically it will be in mega ohms. Is that point clear? Tell me, yes or no? Is the point clear or not? Huh? Is the point clear or not? Okay. Now, we'll go to the next topic. So, differences between ideal diode and practical diode. So, what do you mean by ideal diode and practical diode? What ideal diode will do? The cut-in voltage is 0. Of course, the cut-in voltage is 0 for ideal diode. Okay, the cut-in voltage. That is immediately after the 0, the conduction should start. Immediately after the conduction, immediately after 0 volts, that is, if you apply 0.1 volt also, the conduction should start. Not for germanium you need 0.3 and silicon you need 0.7, not like that. Immediately after 0, let's say it's 0.001 also, the conduction should start. The conduction should start. So since for an ideal diode, there is no barrier potential. So as there is no barrier potential, why the current voltage should be 0? Because there is no barrier potential. There is no barrier potential for an ideal diode. For even for any small forward bias voltage, conduction should start. Conduction should start. And then the forward resistance, the dynamic forward resistance should also be 0. What is dynamic forward resistance? RF should be 0. RF should be 0. Continuous voltage should be 0. The reverse resistance is also 0. The reverse resistance. Why this reverse resistance is 0, sir? Is the reverse resistance 0? Dynamic resistance. Just see this. What is reverse resistance? What is reverse resistance? The dynamic reverse resistance is nothing but this, right? I can call this reverse resistance. The static resistance or reverse resistance, what we call reverse resistance is, what should be the value? What should be the value of this RR? OQ. What is OQ? You can see here. So OQ. This is also 0, right? For infinite change in the voltage also we got 0 current. So it is a print mistake. I think this is infinite. Infinite. The diode readily conducts when forward bias. So FB stands for forward bias, not Facebook. Okay, it blocks conduction and reverse bias. The reverse saturation current I0 is 0. This is also important. The reverse saturation current I0 is equal to 0. So, but reverse RR is going to be infinite, and this reverse saturation current I0 should be 0. I0 should be 0. The ideal diode acts as a fast acting switch. Fast acting switch, acting electronic switch. This is the advantage or application, you can say. This is the application. This is the application of a diode. This is the application of a diode. This is the application of a diode. Okay. Next. The practical diode. The practical diode, there is a potential barrier across the junction, and this must be overcome before the diode can conduct. The cut-in voltage or threshold voltage, see, you can have how many names? You have threshold voltage, offset voltage, breakpoint voltage, cut-in voltage. All these are for same. All these for V gamma is approximately 0.2 or 0.3. Some books will have 0.2 volts, some books will have 0.3. Do not worry, both of them are correct. Do not worry, both of them are correct. So most of them will get 0.3 only. Most of them will get 0.3 only. So 0.7 volts for silicon. So here earlier the cut-in voltage was 0. Earlier the cut-in voltage was 0. But here the cut-in voltage is 0.2, 0.3 or 0.7 volts depending on the type of this semiconductor used. Okay. The forward resistance is in the range of few tens of ohms. So the forward resistance earlier was 0. Right? Here it is a few tens of ohms, or let's say 20 ohms, 30 ohms you'll get. Right? Here the reverse resistance is in the range of mega ohms. That's what I told you, right? This is what? Mega ohms. Ideally it should be infinity. Ideally it should be infinite. Ideally it should be infinite. Or I should say, actually this is RR is correct actually. Capital R suffix small r. So the diode conducts when the forward bias and the bias voltage is more than that of the cut-in voltage. That's what it's saying. Conduction will not start immediately. Conduction will start after the cut-in voltage is reached. After the cut-in voltage is reached, this is cut-in voltage is saying. But whereas for this ideal diode, conduction should start immediately. It means conduction should start immediately means what? Conduction should start immediately after 0. So it should start immediately. Immediately it will start, sir. So immediately after 0, the conduction should start. At 0 itself, the conduction should start. Right? This is an ideal diode. This is an ideal diode. So the diode, the practical diode doesn't conduct when reverse biased, right? However, a small reverse saturation current flow, the reverse saturation current for ideal diode was 0. Yes or no? We have to assume this is I naught is equal to 0. But here some I naught exists. Some I naught exists. So which is in the range of nanoamperes per germanium and microamperes per nanoamperes for silicon and microamperes for germanium diode. Germanium diode. If the diode is made up of silicon, it will be nanoamperes. If the it's made up of germanium, it will be around microamperes. It will be around microamperes. Okay. The diode acts as a fast acting switch electronics. Same application. No change. No change in the application. Next. The circuit model of a diode. What do you mean a circuit model of a diode? Every time I can't draw this, right? See, this is the diode symbol. So when you are using this in the circuit, you should represent this equivalent model, the equivalent model. Then only you will solve any solve any circuit, and you will try to find out the voltage and current across the circuit. So what do you mean by analysis? Analysis is nothing but generally what you will do, you will try to find out voltages and currents and voltages, that's it. Currents and voltages, that's it. Is the point clear? Is the point clear? So for that, what you need to do, sir, you have to replace this the diode with its equivalent model, which is equivalent model. It is equivalent model. So how to get that equivalent model? The circuit model of any device is represented by its equivalent model. Yes, I know. A equivalent circuit is combination of elements properly chosen to best represent the actual terminal characteristics of a diode device. So you will be replaced with this diode with their equivalent elements, which will be very much suitable for the it's a device particulars, device characteristics actually. System in a particular operating region. For a given operating region, you should represent the diode with equivalent model. That means you should replace with equivalent elements. The diode is replaced by a model with a battery equal to the cut-in voltage. So what is trying to do, sir? He is trying to replace the diode with a battery, and whose voltage is its cut-in voltage. And the forward resistance of the diode also. You will have a forward resistance of the diode, and then you will have original diode here. So this resistance is nothing but RF. This resistance is RF. So this is the equivalent model, circuit model of a diode. So whenever you are trying to analyze any given circuit, everywhere you have to substitute like this. You should remember that this diode has this much voltage, this much resistance. After causing this much resistance, then only the diode will conduct. Okay, diode resistance. This is in series with the ideal diode. That's what he's talking about. This is anode. This is cathode. This is anode and cathode. If this is anode and cathode, this is an anode cathode. Okay, next. This is what I am saying. Acha, it's already there. So this is cut-in voltage, and this is ideal diode. This is a forward resistance. The above circuit model is called a piecewise linear equivalent circuit. We'll let you know why it is called piecewise linear in the next slides. Don't worry. So if RF is 0, if forward resistance is 0, since for the most applications it is small to be ignored compared with the resistance of other network. So generally what happens is this diode will be, let's say some R resistance is there. It will be in series. The diode will be in series with this, right? Now what happens is if you replace this diode by its equivalent model. So in this previous phase, what we have seen is if RF is equal to 0, if RF is equal to 0, that is forward current is 0. The forward current is 0. So what we assume that for most of applications will think that forward resistance is 0 and it is small and to be ignored when compared with the resistance. So what does it mean, sir? So generally what happens, sir, this diode is connected in a given series with some network, right? Now what happens, this, let's say this is 10K you are connecting. If you replace this diode by its equivalent model, so what happens? 10K in series with, of course we have, just wait a second. This voltage and then the diode, right? So this is, let's say you have 10K in series with 10 ohms. So what happens, sir? This 10K is this can be ignored, yes or no? This can be ignored. That is the reason why what we'll have only this V cut in voltage on the diode, V cut in voltage and diode, V cut in voltage and diode. Okay. Anode and cathode. This is anode and cathode. Just a second. Now, moving on to the next slide. Next slide. What is here? So now here what is assuming is assuming cut-in voltage is 0 and RF is also 0. Cut-in voltage is 0 and RF is also 0. And what happens, sir? Then the equivalent model. The equivalent circuit becomes the circuit model of the ideal diode. So what ideal diode? Ideal diode is always. So how the ideal diode will be? How the ideal diode will be, sir? Ideal diode for forward bias, and the diode is ideal diode is forward bias. What happens, sir? You will always remember this. We assume that it's going to be short circuit. And it is reverse biased. The ideal diode is reverse biased. Simply open circuit. Nothing doing. No cut-in voltage, no RF, nothing. Simply we'll assume that open circuit. It is going to be open circuit. Is that clear? Is that clear, sir? This is going to be forward bias and this is going to be reverse bias. This is an ideal diode for an ideal diode. Okay, next. Now this is nothing but all the combination of three. Piecewise linear model, simplified model, and ideal model. You can see for ideal model, conduction for piecewise linear model, we assume that cut-in voltage is not 0, forward resistance is not 0, and reverse resistance is infinity. If this is the case, now what happens? See, you can see here the output is changing linearly. Originally, how it looks, sir? Originally, it should be like this. This is linear. This is linear. Is that looking linear, sir? Is it non-linear? This is non-linear. To do mathematical expressions or some calculations, this is very difficult. This model is difficult. This is going to be V. This is going to be I. This is very difficult. We'll go for this linear model. So piecewise linear model. We'll go for this. And as still you find something different, some difficulty. What happens, sir? We can choose this. V cut is not equal to 0, and RR is, that is RR or RF is going to be RF. This RF is not going to be 0. The forward resistance is 0, and RR is going to be infinity. You'll get the VI characteristics like this. Is that fine? Okay. Now earlier it was a linear. It is now. You can see how you got this. Now here comes third model called ideal model. In case of ideal model, cut-in voltage is 0, forward resistance is 0, but reverse resistance is infinite. If the reverse resistance is infinite, what happens here? Immediately after zero, the conduction starts. Immediately after zero, conduction starts. But in case simplified model, after it is crossing cut-in voltage, it starts conduction. Here also, after crossing conduction, the conduction starts for piecewise linear model, but the current changing with respect to voltage very linearly. But here it will be sudden change in the current. So piecewise linear model, simplified model, ideal model, ideal model. Sir, when you want to do some practical circuits, always go for this piecewise linear model. Go for this piecewise linear model. If you want accuracy, go for piecewise linear model. If you're not bothered about accuracy, go for simplified model. If you're not bothered about accuracy and everything, just you want to do it for simplification purpose, go for ideal model. Go for ideal model. If you want to do something in the laboratory, always remember, you should do it. You should do it like this. For perfect channel, you should do it like this. Okay. Now, so we have problems now. Okay. So this problem, we'll try to solve some simple problems. A silicon PN junction, biased with a constant current, at room temperature. When the temperature is increased by 10 degrees centigrade, the forward bias voltage across the PN junction. So he's asking simply, okay. So he's simply asking very simple, sir. Oh, it is very. He's asking simply, what is dV by d naught? What is dV by dt for 10-degree rise in temperature? So we know that for 1 degree rise in temperature, that just now we discussed, yes or no? This is going to be 2.5 millivolts per degree centigrade. So for 10 degrees centigrade, what it will be, sir? For 10 degrees centigrade, what it will be? For 10 degrees centigrade, it will be 10 times of this, minus 2.5 millivolts. So it's going to be minus 25 millivolts. So what do you mean by this minus, sir? Minus sign indicates cut-in voltage decrease. Cut-in voltage decreases. Is that point clear? Simple problem, yes or no? Very simple problem. Okay. Is that okay? Very simple problem, sir. Cut-in voltage decreases. So what is the answer? So D is the right answer. Okay. Next. Here comes problem number 3. This is going to be 300 print mistake. At 300 degrees Kelvin, this also I think some previous gate problem this is. I don't remember that year. I'll let you know tomorrow. At 300 degrees Kelvin, for the diode current of 1 milliamp, a certain germanium diode requires a forward bias of 0. This is cut-in voltage, okay. Whereas a certain silicon diode requires this voltage 0.718 volts under conditions stated above. The closed approximation of the ratio of reverse saturation current in germanium diode to that in silicon diode is asking. He's just asking you to calculate the ratio of I naught GE by I naught SI. So you will do it right. He has given the values. Temperature he has given. He has given the voltages V volt and V volt, and try to calculate what is this. Right? This you do it like a homework. Homework problem one. Simple problem, sir. This is very simple problem. You need not worry. Very simple problem. Do it at your home. Do it at your home, and post it in the comment box. Post it in the comment box. Next, find the current flowing through a silicon diode having this I naught. I naught. This reverse saturation current is 6 microamperes. 6 microamperes for 0.3 volts. Acha, he's asking very simple, sir. He's asking I value is asking. That is I1 and I2 is asking. For different values of I0 he has given, it is 6 microamperes, and he has given a voltage of 0.2 volts and another voltage, let's say V1. The V2 is going to be 0.3 volts. He's asking you to calculate I1 and I2. I1 and I2, very simple. I1 and I2, very simple. Very simple. You can do it and let me know. This also I understand as it is considered this as a homework number 2. Homework number 2, and post it in the comment box. Post it in the comment box. Okay. So that's it. That's it for the day. That's it for the day. Now this is the Telegram channel where I'll post this Telegram channel where I'll post all the notes. Unacademy GATE Telugu. I think already I have posted everything. So many of you already posted all the. Many of you already downloaded all the notes of Unacademy GATE Telugu, right? Generally, I post it as a EDC class notes. EDC class notes by Shravan sir. Class notes by Shravan sir. I'll generally Shravan Kumar sir. Generally, I'll post it like this. Shravan Kumar sir, right? Okay. Okay. Next, these are our YouTube channels. Other YouTube channels also which we have. I would request all of you to like and subscribe for this. So this Creatrix Gate for EE, ECE and IN students and instrumentation students. Unacademy Gate ME mechanical. This is for PI. PI stands for production engineering and engineering sciences. This other channel. And Unacademy Gate Civil Engineering. Unacademy Gate Civil Engineering, a separate channel is there. So engineering Pathshala is there. This is also very important. Unacademy Computer Science. This will be useful for computer science and IT students. Both of them. This will be useful. Unacademy Gate Questions. This is a super channel. So all the previous year Gate questions most probably will be for all subjects will be available on this Unacademy Gate Questions. Unacademy Gate Questions. Very important channel. We have electrical junctions for electrical students. So this is Unacademy GATE Telugu channel where I am teaching right now EDC. So along with this EDC, in parallel, the subjects are going on. The subjects are maths is going on. Maths classes are going on. So communication systems. Senior most faculty members are teaching these subjects. Communication systems. You have. I think you have digital also senior most faculty members. All the faculty are very much senior faculty members, right? So maths, communication, digitals, aptitude is going on. So all these things are going on in Unacademy Telugu. Please do subscribe, and get notifications from this, right? Notifications from this. So very important, sir. Very important. Very important to subscribe. Very important to subscribe, right? So thank you, sir. Happy Christmas in advance. Don't worry, tomorrow also we have class. Happy Christmas, Happy Christmas, Happy Christmas, and Merry Christmas. So in advance, but still we have a class tomorrow. So yes, still we have a class tomorrow, right? We'll catch up tomorrow. We'll catch up tomorrow. Okay, we'll catch up tomorrow, right? So please don't forget to like, share, subscribe, and then hit the bell icon button so that you'll get all the notifications. So happy Christmas in advance, right? So good night. Catch you tomorrow. Right? Bye.